I'm Gabby, and this video will cover the derivation of the heat diffusion equation for Cartesian and spherical coordinates. First we will do the Cartesian coordinate system. I like to list out all my variables before I start a problem. So I have density, specific heat, thermal conductivity, which is how well the material conducts heat, thermal diffusivity, which is the rate at which heat flows through the material, heat flow, and heat flux. And I drew our volume example for our Cartesian system with the x, y, and z coordinate plane. So our primary equation that we will be working with to start the derivation is energy storage is equal to energy generation plus energy flow in minus energy flow out. Energy storage is equal to density times specific heat times the volume, which is dx, dy, dz, times the change in temperature over the change in time. The energy generated is equal to the heat flow for the volume, and then the energy in, as shown in the diagram, is equal to the flow in the x plus the flow in the y plus the flow in the z, and the energy flow out is equal to the flow in the x plus dx plus the flow in the y plus dy plus the flow in the z dz. So looking at our example volume, if you look at this is the x-axis, the y-axis, and the z-axis. So the flow in plus the change in the position of x makes the flow in the x plus dx. Same for the z and y directions. So I'll write out the full equation. I wrote out the equation by subbing in BST, Egen, En, and E out. I went ahead and used a Taylor expansion to separate into the partial derivative. This is a partial derivative and this is not, so these do not cancel. But we can start simplifying. The flows cancel out. I should have used red. And then we can simplify the heat flow partial derivative to further simplify. The heat flow is the area times the flux of the flow, and if we're using the x as an example, the x flow is moving through the yz plane, which is this face of the rectangle, and that would mean the area is dz dy times the flux of the x flow, which is the thermal conductivity constant. This is not always constant, but for this example it will be constant, times the change in temperature relative to the change in the x position moving across the shape. I will write out the next equation with the simplifications and plugging in our new value for the flow. I wrote out the equation, taking out the flows that canceled and inserting our new flux for each section. The area for the y direction would be the zx, and for the y, or for the z, it would be the xy planes. Then the next thing we can do is that every section of the equation, every term, has dx, dy, dz, so those will cancel, and we can rewrite the new simplified equation. Because the thermal conductivity is constant in this case, we can pull it out and divide every term by the thermal conductivity. This term right here is equal to the inverse of the thermal diffusivity, and we can simplify this term with this, and we can simplify how these are written to make the equation look a little nicer. This is the final heat diffusion equation for Cartesian coordinates. Let's check the units of our final equation. We have Kelvin per second, and then we have second per meter squared equals, this is a constant, so I'm not going to worry about the units, Kelvin per meter squared minus Kelvin per meter squared minus Kelvin per meter squared. The seconds cancel, so it's Kelvin per meter squared on both sides of the equation. Now that we have all the math done, I want to do a quick conceptual of the heat diffusion equation. The heat diffusion equation tells us how much energy it takes to raise a volume, a Kelvin, per time as a rate. So the density times the specific heat gives us the amount of energy it takes to raise a unit volume, 1 Kelvin. Multiplying by the volume gives us the amount of energy it takes to raise the volume, a unit Kelvin. And multiplying it by the change in temperature with change in time gives us this as a rate, this energy. And all of this math just makes the equation easier to work with and more simplified, but we are figuring out the rate at which the energy takes to raise the volume a Kelvin or multiple Kelvin. Alright, we're on to the derivation of the heat diffusion equation for spherical coordinates. Thankfully, it will be similar, slightly more difficult math-wise, but very similar process to Cartesian coordinates. This is a section of a sphere, and this is our coordinate system with y, z, x, but we have r, theta, and phi, which is between z and r sine theta. And if we're looking at this diagram, the sides of our shape cut out of the sphere are r sine theta, and theta r. So this is dr, and then d phi, which is being represented by r sine theta, and d theta r theta. And phi and theta are not units of measurement, so they do not correspond to the length or position of a side because it's not a length. The heat flow in the phi direction will be going this way. So on this side it will be the heat flow in the phi direction plus d phi. This way would be the heat flow in the radius direction, d radius, and then the heat flow in the theta, d theta. We have our same principal equation, same setup where it's density, specific heat, and then the volume, and we'll get into the volume in a little bit, and then the energy generated, the flow times the delta volume, and then E in is the flow in the R plus the flow in the theta plus the flow in the phi, and E out is equal to the flow in the R dr plus the flow in the theta d theta plus the flow in the phi d phi. As mentioned previously, the volume is not just r theta phi, it's dr, r d theta, and r sine theta d phi. And this will plug into these equations, so we can write out the extended equation. This is the full extended equation, and we will do similarly to the Cartesian coordinates, where we take the partial derivatives heat flow and make it into the area times the heat flux, so extending it. The R is still very similar, the area not that the heat flow of the R is going through is this panel, which is r d theta and then r sine theta d phi. Times the thermal conductivity constant, dt over dr. This can be simplified to r squared sine theta d phi k dt dr. For q phi, we get dr d theta r from dr, and then d theta dr times k dt over, and because again d phi is not a unit length, we use the entire length as this is the position it's moving along, so you could take the heat diffusion equation at any position on this line, which is r sine theta d phi. And lastly, we have the theta, which is moving along dr r sine theta d phi. Similarly, we're going to use r d theta as that's the position we are moving along. Now I will plug these in to the partial derivatives, and then we can start making cancellations. Alright, I went ahead and plugged these in the partial derivatives and canceled out the flow as we did with the Cartesian coordinate system, and now we can similarly go ahead and divide by the volume as we did previously, and I will go ahead and write out that next step. I wrote out the next simplification. I missed the d temperature, d time here and here, but I added it back in, and it should also be up here. The next step will be to divide everything by k, and I will write that out. I wrote out the next step, and just a reminder that 1 over the thermal diffusivity is the density specific heat over thermal conductivity, which is again constant for this example, but is not always constant. And this is the final equation for the spherical coordinates. Conceptually, it's the same as the Cartesian coordinates, where it's the flow throughout the volume. Thank you for watching, and I hope you learned something.